as long as a function is continuous on an open interval, then we may evaluate the limit simply by evaluating the function at x equals a. So some examples of this, our first function here is 5x minus 1. That's just a slope-intercept line that is going to be continuous everywhere. And so if it's continuous everywhere, we should be able to just plug in the value of 2 in for x and use substitution to find this one out. So this would be 5 times 2 minus 1, which is 10 minus 1, or 9. And so the answer to that one would be 9. The absolute value function, we've looked at that before. That is going to have a shape like that and definitely continuous everywhere. So again, we should be able to just substitute in our our limits approaching here, 3 in for x, and evaluate this. So we got absolute value of 2, which is 2, and that would be the solution for that one. Our third one here, this one may not be quite continuous everywhere, but I think it is at pi over 6. So let's try it just to check. If we plug in pi over 6 here, we're going to end up with cosine of pi over 6 all over sine of 3 times pi over 6. Let's do a little simplifying first. 3 goes into 3 once, 3 goes into here 2 times. So now what we're going to do is figure out what's cosine pi over 6 and what is sine pi over 2. Cosine pi over 6 is like 30 degrees. So if we're doing cosine of a 30-degree angle on the unit circle, that means our hypotenuse is 1 because it's the unit circle. This opposite side should be 1/2 because it's always half that amount. And this one should be times square root 3, so it should be square root 3 over 2. You could do it on the calculator as well. Make sure you are in radians mode here, so check that you are indeed in radians, and this one is. So if we do cosine of pi over 6, we do get that approximation for square root 3 over 2. Pi over 2, that's 90 degrees on a unit circle. That's going to be straight up. And we know on a unit circle, if we're talking about 90 degrees, that would be right here. Sine is the y value. That's going to be the 0.01. And so sine of pi over 2 should equal 1. So we're going to end up getting square root 3 over 2 over 1, which just equals square root 3 over 2. So this one is continuous at that point. Now, that won't always work. Unfortunately, lots of functions are not continuous at all points, and so the answer might not be so obvious. Here's an example function here. If we were to put 2 in for this x here, our denominator is going to turn into 2 times 2 is 4. 4 minus 4 equals 0. We can't have division by 0, and so using substitution doesn't work because our function's not continuous at 2. So what we're going to do on this one is we're going to see what's happening right around 2 to maybe approximate what that limit is. So on our calculator, what we're going to do is go to our y equals. We're going to enter that function in. I'm going to use some parentheses here. So we got x squared plus x minus 6. Close that up and then divide it by parentheses, put the denominator function in, 2x minus 4. And then what we're going to do is go to our table set, and that's in the blue here. So I'm going to hit our second button in this window one. And what we're going to do is we're going to change this independent variable to ask. That way when we go to our table over here on the right, that's our graph. We'll come back to that. We go to our table here. We can input what we want. So what if we put in 1.9? What does our output become? It looks like we get 2.45. And we're going to continue that over here. So we're going to fill in the rest of these by, again, typing them in just to show you one more, 1.99. We get this. So I'm going to, you can pause quick, fill the rest of it All right, so I kind of went through and did the rest of them. You can double check them with your calculators. But now, what do the values in this table suggest? So what are these, as we're getting closer and closer, these numbers are getting closer and closer to 2. And same thing here, 2.1 is kind of far away, 2.01 is closer, 2.001, that's closer to 2. So again, we're both sides are kind of going closer and closer to 2. What do these numbers suggest this is approaching? Well, I would say that it looks like this limit, as we're doing this, is approaching 2.5. Both of those numbers seem to be kind of dialed in and going closer to 2.5. So it looks like this limit approaches 2.5. Well, how can we, or why does this happen, or what's going on here? Well, let's kind of go to the graph here. So I'm going to go back to our calculator. Let's graph it. And for this one, I'm going to hit the zoom button in the middle. We're going to use this number 4 one, the decimal graph, and see what is happening at 2. So if we locate where 2 is, which is right 2 spots away, and we follow it up, you can see on the graph there it appears to be a hole there. So this one does have a hole going on at that location. And so the reason that this one isn't working here, the reason that we get what we get is that this one has a hole in that spot. So now how do we show that the value is 5 or 2.5? Well, we're going to use some algebra here. And what we're going to go back to do is some of the stuff you learned in pre-calc and calc, and is that's to do some algebra or some factoring here. So what we're going to do is factor both the top and bottom. The first one's a trinomial, so it should factor into 2 binomials. We know that the first one's got to be x and x, so multiply that at x squared. What's going to times to equal -6 and add to 1? Looks like +3 and -2. On the bottom, that's not a trinomial, but there is a greatest common factor we can factor out of 2. Leaving x minus 2 remaining. Well, now we can see here if we would cancel out the part that is giving us the trouble, and this is the part giving us the trouble in the denominator, because if we put 2 in there, 2 minus 2 is 0. If we get rid of that and see what this function is kind of equivalent to, now we have x plus 3 over 2. Now plugging in 2 doesn't make a difference. We're going to get 2 plus 3 or 5 halves, which is the same as 2.5, and that's the same result we had gotten before. So does our analytical work confirm our answer? Absolutely yes.